4.5 Integration by Substitution, Part 1, Change of Variable U-Substitution for Finding Indefinite Integrals. Southwestern College, Professor Maria Olivas. Integration by Substitution, Part 1, Objectives. Use change of variables, U-substitution, to find indefinite integrals. We will start with a review of fundamental theorem of calculus, basic antiderivatives. And we're going to begin with some formulas. We're going to start off with our first formula, and that's going to be the power rule for integration. So let's go ahead and start writing down that formula. That formula is going to be the integral of x raised to the n power dx is going to be equal to x raised to the n plus 1 power all over n plus 1. And then to the side of that fraction, we're going to write plus c. And then inside parentheses, underneath this formula, I'm going to write down n cannot equal -1, because if n is equal to -1, then that would be undefined. I'm going to go ahead and box this entire thing in, and that's going to represent our first formula. I'm also going to lasso it and just make it slightly smaller and move it slightly more to the left-hand side so that I have a little bit more space for my other formulas. My next formula is going to be the integral of x raised to the -1 power dx is going to be equal to the integral of 1 over x dx, which is equal to the natural log of the absolute value of x plus c. So we're going to go ahead and box that in. I'm going to lasso that whole thing in. I'm going to make it move upwards a little bit more so I have more space. And then our next formula is the integral of e raised to the x power dx, which is equal to e raised to the x power plus c. And let's box that in. And I'm also going to lasso that in, make it a little bit smaller so I have a little bit more space. And our other formula here is the integral of e raised to the kx power dx, which is going to be equal to 1 over k times e raised to the kx power plus c. Let's box that one in. And now I'm going to go ahead and lasso all of my formulas that I just wrote down in the boxes, and I'm going to make that all smaller and now move it down slightly towards the lower left-hand side of this little section here. I'm also going to number these because there are lots of formulas here. So I'm going to label these formulas. I'm going to label the first one as the integral of the x raised to the n dx, the power rule one, number 1. The one of the integral of x raised to the -1 power dx, that's number 2. And then the two ones that we had for our exponential functions, I'm going to label those as 3a and 3b. All right, practice, evaluate each integral. Number 1, the integral of, we're going to open up a set of parentheses there, x raised to the 5th power plus 9x squared, close the parentheses, dx. So we're going to start off here using our power rule. So that's going to be x to the 6 over 6 plus 9x cubed over 3 plus c. We can simplify this a little bit. So this is going to be equal to x to the 6 over 6 plus 3x raised to the 3rd power plus c, and we will box that in. Number 2 is the integral of 4 over 3 times t raised to the 5th power dt. So the first thing we're going to do for this is we're going to rewrite that t that's raised to the 5th power in the denominator, and we're going to write it in the numerator. So I'm going to write this as the integral of 4/3. The t is going to be written out to the side of that fraction, and that t is going to be raised to the -5th power dt. And this is going to be equal to 4/3 times t raised to the -4 power over -4 plus c, which is equal to -1/3 t raised to the -4 power plus c. And if you would like to bring that t to the -4 power to the denominator, then that would be equal to -1 over 3 times t to the 4th plus c out to the side. All right, let's box in that answer, and I'm going to lasso everything there and make it just slightly smaller so it fits a little bit nicer in that area. Number 3, the integral of 8 over y dy. This is going to be equal to the integral of 8 y raised to the -1 power dy. And this would be equal to 8 times the natural log of the absolute value of y plus c. And we'll box that in. And then number 4 here, the integral of 4e raised to the x power dx is going to be equal to 4 times e raised to the x plus c. And then we could just box that in, and we're done with those problems. Section 2, review. Derivative of composition of functions. Recall, to take the derivative of a composition of functions, we used the chain rule. Example 5, d dx of, open a set of parentheses, x squared minus 3, close the parentheses, raised to the 4th power is equal to. Before I do this problem, I'm going to go ahead and put a cloud around the words the chain rule, because here we really need to remember to use the chain rule. I need to know how to identify my inner function and my outer function. In this case, the inner function is going to be the x squared minus 3, which I'm going to highlight in yellow. I'm going to also go ahead and refer to this as a u. So this is going to now be u to the 4th. And this is going to, if I were to take the derivative of u to the 4th, that would give me 4u raised to the 3rd power, du. And I'm going to go ahead and draw a little brace above the x squared minus 3 with a u above it to show that I've basically substituted u for that. So now that derivative is going to be equal to 4 times, open up a set of parentheses, x squared minus 3, close the parentheses, all raised to the 3rd power times 2x, because the derivative of the inner function is 2x. And now we're going to have here this equal to 8x times, open up a set of parentheses, x squared minus 3, close the parentheses, all raised to the 3rd power, and I'm going to just box that in as our answer. So the key part here was we needed to use the chain rule in order to do this problem. We found the inner function, which was that x squared minus 3. We replaced that with a u, and then we were able to find our outer function, which was basically that u to the 4th. We took the derivative of the outer function first, the u to the 4th, which ended up being 4u cubed du, and then we took the derivative of that inner function, that x squared minus 3, which ended up being 2x. So this is going to be a key part to going forward in this section in order to learn that new technique, that new integration technique that we will be learning. So this means that the integral of 8x times, open up a set of parentheses, x squared minus 3, close the parentheses, all raised to the 3rd power, dx is equal to, open up a set of parentheses, x squared minus 3, close the parentheses, raised to the 4th power plus c, box that in. So by doing this, it helps us see the relationship of how when we take the antiderivative of the derivative, we come back to that original function. Of course, with the addition of the adding of the constant c. And we want to keep this in mind, so what we're going to be doing next is we're going to be practicing that. So we're going to be writing out this relationship to get used to that idea. Practice. Find each derivative, then write a corresponding integral to represent the relationship. Number 6, we have y equals quantity, open up a set of parentheses, 4x plus 3, close the parentheses, all raised to the 5th power. I drew a cloud around find each derivative, and then I'm underlining the part that says then write a corresponding integral. So it's actually got 2 parts to each one of these practice problems. So I'm going to start off by writing dy dx is equal to, And remember, we're using the chain rule. 5 times, open up a set of parentheses, 4x plus 3, close the parentheses, raised to the 4th power, times 4, which is equal to 20 times, open up a set of parentheses, 4x plus 3, close the parentheses, raised to the 4th power. That's the derivative part. Next is the integral part. The integral of 20 times the quantity 4x plus 3 raised to the 4th power dx is going to be equal to, open up a set of parentheses, 4x plus 3, close the parentheses, raised to the 5th power plus c. And I went ahead and I boxed in that entire relationship. So that part where it says the integral is equal to the antiderivative, right, plus c. I went ahead and boxed that whole thing in, and I also boxed in the part where we found the derivative. Okay, number 7. Y equals 4 over the square root of 2x minus 3. First, we're going to rewrite this. We want to rewrite this so that we write what's in the denominator up in the numerator, and we also want to rewrite it so that the square root is written as an exponent. So I'm going to write y equals 4 times, open up a set of parentheses, 2x minus 3, close the parentheses, all raised to the negative 1/2 power. This is going to be much easier to find the derivative of. So I'm going to go ahead and use the chain rule. So this is going to be the derivative of y equals negative 1/2 times 4 over 1 times, open up a set of parentheses, 2x minus 3, close the parentheses, raised to the negative 1/2 power minus 2/2 times 2. So now we're going to simplify that. The derivative of y is going to be equal to, and negative 1/2 times 4 is going to give me negative 4/2 times, I'm going to bring that 2 that was out and back in front here, times 2 over 1, times, open up a set of parentheses, 2x minus 3, close the parentheses, negative 3/2. And this will then be the derivative of y equals, if we multiply negative 4/2 times 2 over 1, we're going to just end up with a negative 4 times the quantity, 2x minus 3, and then that quantity is going to be raised to the negative 3/2 power. I'm going to box in that derivative. And another way to write this answer, if you didn't want to leave it with a negative exponent, would be this way. I'm going to write that this is also equal to, we could write negative 4 in the numerator of a fraction, and then that would be over, and here we would write a square root, and then inside the square root you would write 2x minus 3, and then I could put parentheses around the entire square root part and just raise it to the 3rd power. And that would be perfectly fine as well if you didn't want to have an answer written with a negative exponent in it. So now we're ready to write down the corresponding integral that represents the relationship between the derivative and the antiderivative. So here it is. It's going to be the integral of negative 4, open up a set of parentheses, 2x minus 3, close the parentheses, raised to the negative 3/2 power dx is going to be equal to 4 over, we're going to open up a set of parentheses, 2x minus 3, close the parentheses, and raise that to the 1/2 power. And then out to the side of this fraction, we will have plus c. So I'm going to go ahead and box in that entire thing all the way from the very start of that integral to the very end of that plus c, because that is the corresponding integral that represents the relationship between the derivative and the antiderivative. I'm going to go ahead and draw a line all the way across here, separating problem 7 from problem number 8. So problem number 8 says y equals e raised to the 3x squared power. So we're going to go ahead and start off by finding the derivative. So I'm going to write this as dy dx is equal to, we're going to take the derivative of this, e raised to the 3x squared, which will end up being e raised to the 3x squared times, and we're going to take the derivative of the exponent part, which will give me 6x. If we simplify this, it's going to come out to 6x e raised to the x squared. So I'm just going to go ahead and rewrite this so that you can see that this is the derivative. I'm going to rewrite this over here on the right hand side as dy dx equals the 6x e raised to the 3x squared. And I'm going to box that in because that is our derivative. Now that we boxed that in, let's go ahead and write our corresponding integral. So we're going to go ahead and write the integral of 6x e raised to the 3x squared power, and then dx. This is going to be equal to e raised to the 3x squared power plus c. We're going to go ahead and box in that entire thing right there, and that's it for problem number 8. So all of these problems were to help us, prepare us to see that relationship between the derivative and the antiderivative. Notice that taking the derivative using the chain rule creates a product. To integrate a product that was created this way, we need to find a way to undo the chain rule. The process used to evaluate these type of integrals involves a change of variables and is called integration by substitution. I have highlighted the words change of variables and I have underlined the words integration by substitution. All right, so let's move on to this part 3 here, indefinite integrals substitution. Example 9. Evaluate the integral of the square root of 4x plus 1 dx. We're going to start off with step 1 here. Step 1 is identify the inner function of a composition, and we're going to call this u. So in order to identify the inner function here, and I am putting a cloud around the word inner, it's very important that you know which one is the inner, which one is the outer function. So the inner function in this case is going to be the 4x plus 1. I'm going to rewrite the integral here on the right hand side. So I'm going to write the integral of the square root of 4x plus 1 dx. Now I'm going to highlight the inner function, which is the 4x plus 1. I'm also going to put a cloud around the inner function so that it really stands out, and draw an arrow pointing towards that inner function, and then write down the words inner function next to the arrow. So there should be no confusion here. Which one is our inner function? I'm going to write here to the right, u equals 4x plus 1. So now we're going to go ahead and find our second step here. We're going to find du, which is our step 2. So I've highlighted step 2. Step 2, find du. I'm going to go over here to the right hand side, right under where I wrote u equals 4x plus 1. I'm going to write du dx equals 4, and it's just 4, right? Because the derivative of 4x plus 1 is just 4. I'm going to draw a little arrow here to the side, and I'm going to write this as du is equal to 4 dx, because we can rewrite it that way. Now that we rewrote the du here, I'm ready for highlighting du equals 4 dx. That's very important that we know what that is. And now we're ready to move on to step 3. Step 3 says substitute everything in the original integral with an expression involving u or du. I have gone ahead and highlighted step 3. So now we are ready to do that step right here. So now I'm going to rewrite du equals 4 dx, and I am going to solve for dx by dividing both sides of the equal sign by 4. The 4's on the side with the dx will cancel out, or they will divide out and turn into 1, and I will have, I drawn an arrow to the right, I will end up with dx equals 1/4 du. So this is what I'm going to replace in place of dx. So I have underlined the dx in the integral. I have drawn a cloud around the 1/4 du, which I'm going to substitute in place of dx. And I'm writing down the words substitute for dx with an arrow pointing towards the dx, right? I've highlighted the dx in green, and I've also highlighted the 1/4 du in green to see exactly what is going to be substituted in place of dx. So before I replace everything in terms of u and du, I want to rewrite my integral so that I have an exponent written in place of that square root. So I'm going to go ahead and write the integral of, I'm going to open up a set of parentheses, I'm going to write 4x plus 1, close the parentheses, and raise that to the 1/2 power, and then write my dx. And I just rewrote my problem so that I had an exponent in place of the square root. I've highlighted the 4x plus 1 with a yellow highlighter and the 4x plus 1 where it was equal to u. And I've also highlighted the dx in green highlighter. And now I am going to rewrite everything in terms of u. So it'll be the integral of u raised to the 1/2 power times 1/4 du. And now I have done my u substitution. I'm putting a red cloud around the 4x plus 1, and I'm putting an arrow pointing down to the u that I replaced it with. And I'm also drawing a green cloud around the dx, and I'm pointing an arrow down towards the du to see. So now I'm going to rewrite this with the 1/4 factored out times the integral of u raised to the 1/2 power du, which is equal to 1/4 times u raised to the 3/2 power divided by 3/2 plus c. Now we just need to simplify this. I'm going to just erase the part where the page number is here so I have more space to write on. So now we're going to, and by the way, I just did the last sentence in the step 3, integrate this new integral. So we just did that. Okay, I've drawn an arrow pointing to my next step. It's going to be 1/4 times 2/3 times u raised to the 3/2 power plus c. So let's simplify this a little bit more. I think I can simplify the 1/4 times the 2/3 here. So that's going to simplify to 1/6. And then that's going to be times. I'm going to replace the u with 4x plus 1 in parentheses, all raised to the 3/2 power, and then plus c out to the side, and we're going to box that in. And that would have been our step 4, which was substitute back the original x expression for u. So I'm going to go ahead and highlight the steps that I did. I highlighted in yellow the integrate this new integral. I'm highlighting in blue step 4 where it says step 4, substitute back the original x expression for u. And we are done with that problem. Now let's go into some generalized integration formulas, and let's start off with our number 1 rule here, our power rule. We're going to write down the integral of u raised to the n power du is equal to u raised to the n plus 1 power divided by n plus 1 plus c out to the side, so long as n is not equal to -1. Our second rule here for exponential functions, the integral of e raised to the u power du is equal to e raised to the u power plus c. Or you might have something that looks more like this. The integral of e raised to the ku power du is going to be equal to 1/k times e raised to the ku power and then plus c out at the end. Number 3, natural logarithm. If we've got something that looks like the integral of 1/u du, which is also equal to the integral of u raised to the -1 du, then that's going to be equal to the natural log of the absolute value of u plus c. I'm just going to go ahead and write one big square bracket over here on the right-hand side containing all of these formulas, and I'm going to write a little star and the word memorize next to them so that you remember to memorize these, and I'm going to underline memorize twice. Let's go ahead and do some examples, but before I do some examples, let me go ahead and box in each one of these rules so that you don't forget them. Examples. Evaluate each integral. Number 10, the integral of e raised to the 5x power dx. So for this problem, what we need to do first is we need to identify what our inner function is going to be, what we need to set equal to u. So here we have e raised to the 5x power. The 5x that's in the power, in the exponent, that's going to be our inner function. I'm going to highlight that in yellow, and I'm going to point an arrow at the 5x. And next to the arrow, I'm going to write down the words inner function, so you guys know exactly which is our inner function. Now I'm going to write down u equals 5x. Next, we need to find the derivative, so I'm going to find du. Du is going to be equal to 5 dx. Now we need to solve for dx, so that's going to be equal to 1/5 du is equal to dx. So dx is equal to 1/5 du. I'm going to replace that dx with a 1/5 du. So now we are going to have the integral of e to the u power times 1/5 du. Now we can integrate this. I'm going to factor out the 1/5 in front of the integral sign, and then we're going to have the integral of e raised to the u power du. So this will be 1/5 times e raised to the u power plus c. Now I can replace the u with 5x. So that'll be equal to 1/5 e raised to the 5x power plus c, and I'm going to box that in, and we're done for that problem. Number 11, the integral of 1 over, and we're going to open up a set of parentheses here in the denominator, 3x minus 5, close the parentheses, raised to the second power, and then dx out to the side. I've highlighted the 3x minus 5 because that's going to be our inner function. So I'm going to write down u equals 3x minus 5. Du is going to be equal to 3 dx. Now we solve for dx. So I'm going to divide by 3 to both sides. So we'll get 1/3 du is equal to dx. And now I can replace my dx with that 1/3 du. So dx is equal to 1/3 du. Let's go ahead and rewrite our integral in terms of u. So it'll be equal to the integral of, we're going to open up a set of parentheses, 3x minus 5, close the parentheses, and I'm going to write the exponent here as a -2, and then dx. And then I can write this as the integral of u raised to the -2 power times 1/3 du. I'm going to factor out the 1/3 in front of the integral sign. Then we'll have the integral of u raised to the -2 power du. And this will be 1/3 times u raised to the -1 power divided by -1 plus c. And this will simplify to -1/3 times, open up a set of parentheses, 3x minus 5, close the parentheses, raised to the -1 power plus c. Or if you don't like that -1 power, we could write negative in front of the fraction sign and then 1 over 3 times the quantity 3x minus 5 and then plus c at the end. I'm going to just box the one that doesn't have the negative exponent, but you could use either one. Number 12, the integral of 3x squared all over the square root of x cubed plus 4 and then dx out to the side. So here we have to be careful with what we choose as our inner function. I'm going to choose the x cubed plus 4. If we choose u equal to x cubed plus 4, notice what happens when we take the derivative. We're going to get du equals 3x squared dx, and we happen to have a 3x squared in the numerator of this function. So that's going to work out perfectly for us when we do our substitution. So now what I'm going to do here is I'm going to rewrite my integral as the integral of 3x squared times the quantity x cubed plus 4 all raised to the -1/2 power dx. If you notice here, I've got the 3x squared in front of the parentheses here, and I've got the dx. And that's exactly what I have du equal to here. What I'm going to do is I'm going to rewrite my integral so that I write the 3x squared right next to the dx, so you can see that they are exactly the same, and just kind of move this over because it's multiplication is commutative, so I can switch the order of the factors here. So this is going to be equal to the integral of, open up a set of parentheses, x cubed plus 4, close the parentheses, raised to the -1/2 power times 3x squared dx. So I think this is more clear for you to see that I have the 3x squared and the dx right next to each other. Now I can replace that whole thing with a du when I do my u substitution. I'm going to write a cloud around the 3x squared, around both of them, the one that's equal to the du and the one that's in the integral. And I'm also going to highlight the du and put a cloud around it so you can see that I'm just going to go ahead and substitute du in for 3x squared dx. I'm highlighting in yellow the x cubed plus 4, and I'm also highlighting in yellow the u that is equal to the x cubed plus 4. I'm drawing a cloud around the u and an arrow pointing at the x cubed plus 4, so you can see exactly where I'm going to substitute that. So this is going to be equal to the integral of u raised to the negative 1/2 power du. So that's going to be equal to u raised to the negative 1/2 plus 2/2 power. If I add negative 1/2 plus 2/2, it's going to be equal to positive 1/2. I'm going to write that in the denominator. And then plus c, and that's going to be equal to 2 times u raised to the 1/2 power plus c. I'm going to go ahead and substitute back in for u. U was equal to x cubed plus 4, so it's going to be 2 times, open up a set of parentheses, x cubed plus 4, close the parentheses, raised to the 1/2 power plus c. Or you could also write it as 2 times the square root of x cubed plus 4, and then plus c outside of the square root. And we're going to box that in. I'm going to go ahead and make all of this work just slightly smaller. So I'm going to lasso in all the work that I just did here for problem number 12, and I'm just going to shrink it a little bit so that I have a little bit more space here for number 13 so that the work isn't colliding with the work from number 13. Number 13, the integral of 1 over 7x plus 3 dx. So I think by now you've discovered the importance of identifying the correct inner function. Here our inner function is going to be that 7x plus 3. So we're going to set u equal to 7x plus 3. du is going to be equal to 7 dx. I'm going to have to solve for dx in this case, so we're going to divide both sides by 7. So it'll be 1/7 times du is equal to dx. So here I have the integral of, I'm going to write, open up a set of parentheses, 7x plus 3, close the parentheses, raise it to the negative 1 power dx. So this is going to be the integral of u raised to the negative 1 power times 1/7 du. So that 1/7, I'm going to go ahead and factor that out in front of the integral sign. So we're going to have that equal to 1/7 times the integral of u raised to the negative 1 du. So this should look very familiar to some of the formulas we were just talking about earlier. So I'm going to be able to use one of those formulas here. This is going to be equal to 1/7 times the natural log of the absolute value of u plus c, which is going to be equal to, or maybe not exactly equal here, maybe I should do out an arrow since I'm doing a substitution here. It's going to be 1/7 times the natural log of the absolute value of 7x plus 3, close the absolute value, and then plus c, and we're going to box that in. Number 14, the integral of 5y over the quantity y squared plus 5 all raised to the 3rd power dy. So this is going to be equal to the integral of 5y times the quantity, I'm going to open up a set of parentheses here, y squared plus 5, and then we're going to close the parentheses and raise this to the negative 3 power dy. And now I'm also going to rewrite this as being equal to, I'm going to factor out the 5 from the integral. So it's going to be 5 times the integral of, open up a set of parentheses, y squared plus 5, close the parentheses, raise the negative 3 power. I'm going to write the y next to the dy because I'm already anticipating what I'm going to have to do for my u substitution here when I substitute for du. So now we have to choose what our u is going to be. Our u is going to have to be the inner function that we have here. The inner function is going to be u is equal to the y squared plus 5. So now let's take the derivative of this. So our du dy is going to be equal to 2y, because the derivative of y squared plus 5 is just 2y. And now I need to rewrite this. I need to rewrite this in a way that it's going to make this fit nicely here. So I'm going to have du is equal to 2y dy. And I don't have a 2 over here on my problem, so I'm going to divide both sides by 2 so I can isolate that y dy, and then it will substitute in nicely into my integral problem. So here I'm going to have 1/2 du is equal to y dy. And now this is set up nicely for the substitution. So I'm going to replace y dy with 1/2 du. I see here, I got y dy, I've highlighted it in yellow. I've also highlighted it in yellow in the integral problem that we have. And now I'm highlighting in yellow what I'm going to substitute for it, which is the 1/2 du. So we're going to go ahead and replace y dy with 1/2 du. I'm drawing a line here to separate my work. So now I'm going to write on the right hand side of the line, my integral is going to be equal to 5 times the integral of, I'm going to replace that y squared plus 5 with a u, raise it to the -3 power, and then replace that y dy with 1/2 du. Now let's write this a little nicer. I'm going to factor out that 1/2 to the front. So this is going to be equal to 5/2 times the integral of u raised to the -3 power du. So now we can integrate this. This is going to be equal to 5/2 times, and if we integrate u to the -3 power du, we're going to get u to the -2 power over -2 plus c. So we can simplify this. So this is going to be equal to, I can multiply the fractions together here, and I can get -5/4 u to the -2 power plus c. And this will be equal to -4 times, and instead of u, I'm going to replace u with y squared plus 5. I am now highlighting the u and that y squared plus 5 in green, so you can see exactly what I'm substituting right now. So this is going to be equal to -5/4 times, open set of parentheses, y squared plus 5, close the parentheses, raised to the -2 power, then plus c out to the side. I'm going to box that in, and that's going to be our answer. Number 15, the integral of 4t times e raised to the t squared power dt. So let's go ahead and highlight that t squared that's in the power. That's going to be our inner function. So I'm going to set u equal to t squared. Therefore, du will be equal to 2t dt. I see here that I do have a t in there. I'm going to divide both sides here by 2 to move the 2 over to the other side, and I will end up with 1/2 du is equal to t dt. So now I can rewrite my integral. My integral is going to be equal to the integral of 4e raised to the t squared power times t dt. I'm highlighting the t dt in green as I am doing it over here where it's equal to the 1/2 du, and I'm going to substitute that. So this is equal to 4, I'm factoring out the 4 times the integral of e raised to the u power times 1/2 du. That 1/2, I can factor that out, So if I factor that out, it's going to be equal to 4/2, which can be simplified, times the integral of e raised to the u power du. So this is equal to 2 times e to the u power plus c, and if we replace u, this will be equal to 2 times e raised to the t squared power plus c, and we can box that in, and that's our final answer.